Namaste everyone. In this lecture, I will be explaining the properties of action potential. Properties of action potential. So we all know what is action potential. Action potential is a brief sequence of changes in the membrane potential when a stimulus of threshold stimulus or a stimulus of above threshold stimulus is applied. What are the changes in the membrane potential that is happening is action potential. In normal terms, action potential is nothing but the electrical signals that are generated over the cell membrane of the excitable cells. So now we'll list out what are the different properties of action potential. So first property is, for an action potential to be generated, threshold stimulus should be applied. For the action potential to be generated, the strength of the stimulus should be adequate and the duration for the application of stimulus should be adequate. So that is threshold stimulus. What happens if sub-threshold stimulus is applied? Sub-threshold stimulus can only cause slight changes in the membrane potential from minus 70 millivolt to either minus 65 millivolt or minus 60 millivolt. So these are all graded potentials. These are generated when sub-threshold stimulus are applied because of slight leakage of positivity or sodium into the cell, which will not take the membrane potential from minus 70 millivolt to the firing level, that is minus 55 millivolt. So if sub-threshold stimulus is applied, when the sub-threshold stimulus is applied, the membrane potential will not be taken from resting state to the firing threshold levels. So there is slight deflections or slight depolarizing potentials which are generated with sub-threshold stimulus. But when a threshold stimulus is applied, what is happening? So this is the cell membrane. At this area of the cell membrane, when a threshold stimulus is applied, so there is a lot of entry of sodium ions through the leaky sodium channels, so resulting in intake of more and more positive charge, so that the membrane potential from minus 70 millivolt will rise to minus 55 millivolt. So this actual potential, that is around minus 55 millivolt, is the firing level where another set of voltage gated sodium ion channels open up and resulting in rapid influx of more and more positive charge and taking the membrane potential from minus 55 millivolt to rapid depolarization followed by rapid repolarization because of the potassium efflux. So this action potential is generated only when the membrane potential is taken from resting level to the firing level. So from the resting level to the firing level, the membrane potential change can happen only when threshold stimulus is applied. So now we can see what is the property of a threshold stimulus. The threshold stimulus has two components. One is the strength component, strength of the stimulus, and the other one is the duration of the stimulus. So we can explain the relation between the strength and duration in terms of graph, that is strength duration curve. So in x-axis we plot duration in milliseconds. In y-axis we will plot strength of the current in millivolts. So consider now, this is 0, this is 1 millivolt current. So if you apply 1 millivolt current for whatever, how much long duration also, even for hours together, if you apply 1 millivolt current, there is no generation of action potentials over the cell membrane. So now consider with the experiment, you try to increase the current and see whether 2 millivolt current can cause action potential generation, whether it is applied when it is applied for longer duration also. So even 2 millivolt current will not generate any action potential, even though it is applied for long duration also, there is no action potential generation. Now if you consider at a particular strength, consider this is a hypothetical value, at 3 millivolt. So this 3 millivolt current is applied and it is applied for a particular duration. Consider this is some duration under x-axis. Consider this is applied for around 10 milliseconds. Consider this is for 10 milliseconds. When this 3 millivolt strength current applied for 10 milliseconds, there was a deflection, response is seen and action potential was generated. So that means the minimum current is 3 millivolt. So 1 millivolt and 2 millivolt could not generate the action potential, but 3 millivolt strength generated the action potential only when it is applied for 10 milliseconds. These are hypothetical values only. So this lowest strength of the current applied for an adequate time, this is the minimum strength of the current applied for adequate time, there was action potential generation, response is seen. So this minimum current is named Rio base. So minimum intensity of stimulus, that is the Rio basic current, when it is applied for adequate time they have named it as utilization time. Utilization time. When Rio basic current applied for utilization time, action potential was generated, the response was seen. So here we can plot it as, so this strength of the current, this is Rio base. When this Rio base is applied for how much duration? Utilization time. So up to this point, utilization time, and at this point here action potential was generated. So that means whatever may be the strength of the stimulus below the Rio basic strength, whatever may be the strength of the stimulus below the Rio basic strength, for how much ever long duration they are applied, they will not generate response, they will not generate action potential. So for the action potential to be generated, the minimum strength of the stimulus that is should be applied is Rio basic strength, and that should be applied for an utilization time, adequate time, to generate a response. Now in the second experiment, what they did is they increased the strength of the stimulus to double the Rio basic current. Now consider 3 millivolt is Rio basic current, they increased to 6 millivolt. So this is double the Rio basic current. So what happens now? They have increased to 2 times the Rio basic current. The strength is increased to 2 times. Strength is increased to 2 times. Now for how long this strength current should be applied to generate action potential? So this double the Rio basic current to be applied to a adequate time, that is Chronix duration, adequate time to generate action potential. So when double the Rio basic strength of the stimulus is applied for an adequate time, Chronix, action potential is generated. So you can plot the graph this way, and here this is plateau. That means below this level, whatever may be the strength of the stimulus below the Rio basic strength, and how much ever long these strength stimulus is applied, the action potential is not generated. Below this value, no action potentials. And here above here, so here whatever may be the strength here in this region, for this shortest duration action potentials are not generated here. So adequate duration is also mandatory. Not only the highest strength stimulus, adequate duration is also must for action potential generation. So in this region, consider there is around 10 millivolt strength, very high strength. So if high strength given for very few seconds, consider this is 1 millisecond. At 1 millisecond high strength, no action potential generation. You understood this? So you understood the second concept, what is Rio base and what is Chronix, and what is Chronix we'll explain here. So Chronix is the duration, right? Chronix is the duration when 2 times the Rio basic strength is applied. When 2 times the Rio basic strength current is applied, that will generate what? Action potential. You understood this? Yeah. So what is the importance of this Chronix now? So consider there are different excitable cells like nerve cells, neuron, skeletal muscles. So you can compare the values of Chronix. Compare the values of Chronix between the neurons and skeletal muscles. So Chronix is the duration. Chronix is in terms of milliseconds duration for double the Rio basic strength current applied to generate action potential. If the Chronix value is less, that means in shortest duration, double the rheobasic strength in shortest duration, action potential was generated. So you applied double the rheobasic strength with lower Chronix duration, action potential is generated. What does it mean? The cell is more excitable. So lower the Chronix, the more is the excitability of the cells. So neurons are having low Chronix values and the neurons are more excitable when compared to the skeletal muscles. Chronix duration is more, that means more duration of double the rheobasic strength need to be applied to generate action potential. So these are less excitable when compared to neuron cells. So the Chronix is an index for comparison of excitability between the tissues. So this is about the first property, that is threshold stimulus. So next we will move to the second property, that is all or none response. The second property is all or none response. Action potential obeys all or none phenomenon. What does it mean? So whenever action potential is generated, so when the membrane potential from the resting level is taken to firing level, that is minus 55, when all voltage gated sodium channels are activated, and maximum sodium ions are entering, the amplitude will reach to the maximum level, that is plus 30 milliwatt. The amplitude is maximum. So with the threshold stimulus, what is happening? With the threshold stimulus, all the voltage gated sodium channels are getting opened at minus 55 millivolt. Because of activation of all voltage gated sodium ion channels in that region, maximum entry of positive charge into the cell. So there is maximum entry of positive charge resulting in maximum depolarization. So that means this system is working at maximum capacity when threshold stimulus is applied. So now you consider now, if you increase the strength of the stimulus, whether the working capacity is increased. Already the system is working at maximum capacity at threshold stimulus itself. So all the sodium channels are getting opened, maximum sodium ions are entering, and maximum amplitude is already reached, plus 30 with the threshold stimulus. Even though you increase the strength of the stimulus above the threshold stimulus, you call it as supra-threshold stimulus, the amplitude of action potential remains the same, that is up to plus 30 millivolts. So this is nothing but, if the action potential is generated, it is generated to maximum response even with the threshold stimulus itself. So even though if you increase the strength of the stimulus to supra-threshold stimulus, the response will not be a change because it has already given a maximum response. Whether it responds, if it is responding to a maximum level. If there doesn't respond, there won't be any generation of action potential. If action potential is generated, it is generated with a maximum amplitude. If action potential is not generated, there is no response itself. That's all. So even though whatever may be the strength of the stimulus, if you increase the strength of the stimulus also, the amplitude remains the same. So you can draw the diagram like this. Sub-threshold stimulus, there is no action potential generation, no response. Threshold stimulus, action potential generation, and the spike potential is plus 30 millivolt. Supra-threshold stimulus, even the action potential generated will be up to plus 30 itself. The amplitude will be same. And why? What is the reason for the same amplitude? Because at the threshold stimulus level itself, the system is acting with the maximum capacity, all the voltage gated channels are activated and maximum amount of sodium is already entered and amplitude has reached to maximum level itself even with the threshold stimulus only. So this is about all or none phenomenon. Next we will discuss the third property, what is refractory period. What is refractory period? Refractory period is nothing but the time, it is in duration, time interval where the cell membrane which has already responded to first stimulus will not respond to the second stimulus. If you give the second stimulus to the area which is already acting, there won't be generation of second action potential, that is refractory period. So consider now, this is the cell membrane and at this area you have applied a threshold stimulus, and because of the threshold stimulus there is depolarization, repolarization, action potential that is happening. Now if you give the second stimulus when action potential is happening, do you think there is generation of one more action potential? No, there won't be generation of second action potential during this time. So there is a brief period of unresponsiveness of the cell membrane to second stimulus. This refractory period can be divided into absolute refractory period and relative refractory period. What is absolute and what is relative? Let's explain now. See, this is the response of the first stimulus. When first stimulus is applied, what is happening? Action potential depolarization is happening, repolarization followed by hyperpolarization. So this depolarization is because of activation of voltage gated sodium ion channels, influx of positive charge, and here repolarization is because of the potassium efflux of positive charge, negative inside. So now if second stimulus is applied here when already the membrane is in depolarized state, there is no generation of action potential. So this time is refractoriness to second stimulus. If at all the second stimulus is applied here during the repolarization phase, what happens? When the membrane is in repolarization phase, if the second stimulus is applied, still there is no second action potential generation because the voltage gated sodium channels during the repolarization phase are in inactive state. The sodium ion channels are in inactive state during the repolarization phase. So only when the voltage gated sodium ion channels are in resting state, this is the resting state of the voltage gated sodium ion channels where the activation gate is closed and inactivation gate is open. So this is the resting state of the voltage gated sodium ion channels, and when the voltage gated sodium channels from inactive state will switch to the resting state, then only this can be stimulated to open up the gate of the voltage gated sodium ion channel and for the action potential to be generated. So that means during the active state of voltage gated sodium ion channel or during the inactive state of voltage gated sodium ion channels, they will not respond to any sort of stimulus. Whatever may be the strength of the stimulus, the voltage gated sodium channels will not respond. They are already responding to maximum and they are already responding and working for the first stimulus. So that is happening during the depolarization phase and in the early repolarization phase. So in the depolarization phase and in the early repolarization phase, so in this phase, what is happening? Whatever may be the strength of the stimulus, even higher intensity stimulus also failed to generate action potential. So that is absolute refractory period. But during the later part of repolarization, what is happening? Some of the voltage gated sodium ion channels are coming to the resting state. This is the resting state. And when supra-threshold stimulus is applied here during this portion, when supra-threshold stimulus is applied, here, so what happens? This inactive gate can flip open. then resulting in flooding of positivity and action potential can be generated. So with the supra-threshold stimulus during the later half of the repolarization phase, the second action potential can be generated with the second supra-threshold stimulus. This is relative refractory period. So during the relative refractory period, the membrane will respond by generation of action potential, but the strength of the stimulus should be supra-threshold stimulus. It is not the just threshold, it should be very high intensity stimulus need to be applied to generate the action potential in relative refractory period phase. So in timeline, if we explain, so this is the graph, firing level, depolarization, rapid repolarization, slow repolarization. So here this depolarization and early part of repolarization. So this phase accounts to up to this. This is absolute refractory period. And the later part of repolarization phase, this later part of repolarization phase is relative refractory period. So why this portion is said to be absolute refractory period? Because the sodium channels are in inactive state. This is the inactive state of sodium channels. So the sodium ion channels, voltage gated sodium ion channels are in inactive state. So with whatever may be the strength of the stimulus, this inactive state voltage gated sodium ion channel cannot be made open, cannot be activated. So at this point, some of the sodium channels are in resting state. So resting state means outside gate is closed, inside gate is open. So this is the resting state, and here supra-threshold stimulus can flip open and resulting in action potential generation in relative refractory period phase. So this is about the third property, refractory period. Now we'll move to the next property, that is propagation of action potentials. How action potentials are propagated. Propagation or conductivity. So this is fourth property. So fourth property is propagation of action potentials or conductivity. So what does it mean? The action potentials are nerve impulses or electrical impulses which are generated at one point. They are transmitted throughout the length of the nerve fiber until the nerve terminal, axon terminal. Consider this is the axon and this is the axon terminal. And this is a cell body, and this is the initial segment or axon hillock. Consider this is a motor neuron. Action potential in the motor neuron is generated at initial segment. So when a threshold stimulus is applied here, action potential is generated. What does it mean? There is rapid influx of sodium ions through activated voltage gated sodium ion channels. So now this area is getting excited. Action potential is generated in this area. So how the action potential from this area spreads to the neighboring areas? How it spreads to the neighboring areas, we need to understand. See, I have made into so many small pieces of areas. The action potential which is generated here, how it spreads to the neighboring areas, and the action potential has to propagate all along the length of the nerve fiber till it reaches the nerve terminal. So we'll explain now propagation of action potential or spread of nerve impulses. It is similar to that of spread of nerve impulse. Transmission of nerve impulse along the axon. How it happens? Now I'll explain it with an enlarged diagram here. So this is the axon. I have enlarged this, and this is the initial segment where threshold stimulus applied has generated action potential by influx of positive charges through voltage gated sodium ion channels. So this portion of membrane is excited. Now how this electrical impulse which is generated here spreads to the neighboring area. So what happens when there is increased positive ions inside? They start diffusing to the neighboring area. The positive charge start diffusing to the neighboring area. So what was the membrane potential in this area? It was at minus 70 millivolt. It was at minus 70 millivolt resting state because of the diffusion of positive charge from the neighboring. So what happens? This minus 70 is taken to firing level, that is to minus 55 millivolt. So what is the explanation for change of membrane potential in this area from minus 70 to minus 55 is because of slight diffusion of positive charge from the previously excited area. So once the membrane potential reaches the firing level, what happens? There is rapid influx of more and more sodium ions through what? Voltage gated sodium channels that will result in action potential generation here. So what happens? The positivity increases more up to plus 30. So that is how this area, here in this area, an action potential is generated. That means here in the area 1, the action potential or electric signals which was generated created action potential in the second area by electrotonic spread of positive charges, electrotonic diffusion of positive charges to the neighboring area. Now how the third area will get the action potential? So this is like a vicious cycle. The positive charged ions which are here more in number, they diffuse to the neighboring area, and this in this area with the membrane potential which was at minus 70 millivolt will move to the minus 55 millivolt because of this diffusion of positive charge. And at this minus 55 millivolt, what is happening? There is activation of voltage gated sodium ion channels. So the more and more positive charges enter inside the cell because of activation of voltage gated sodium ion channels in this area, resulting in generation of action potential in this area. So this is how action potential wave of depolarization spreads all along the length of the nerve fiber. So now you can again explain how in this fourth region of the cell membrane action potential is generated. So those positive charge which have entered here, will they diffuse here. So because of diffusion of positive charge, the membrane potential which was at resting here from minus 70 millivolt, it is going to minus 55 because of this diffusion. And once at minus 55 millivolt, what happens? There is activation of voltage gated sodium ion channels and rapid flooding of positive charge more and more, and it will become plus 30 here, and action potential is generated in this region. So this is how from one end of the axon to the axon terminal, the other end, the action potential or the electrical signals are propagating. Is that understood? So this is about the propagation of action potentials. This happens in case of what? Unmyelinated nerve fibers. So this is electrotonic conduction. Electrotonic conduction of action potential, electrotonic conduction of action potential in case of non-myelinated or unmyelinated nerve fibers. And the velocity of conduction here is, this is slow process. The action potential which was generated in one place slowly creates an action potential in the next place, slowly creates action potential in the next place, slowly the nerve action potential propagates from one region to the other region. The signals are propagating from one region to the region slowly. So the velocity of conduction here is slow. Now we will explain how action potential is propagated in case of myelinated nerve fibers. Consider this is a fiber, axon fiber, and here the certain regions are myelinated. So consider this is myelinated for this portion. The myelin sheath is covering in this portion, and one more here covering this portion. Myelin sheath is covering, and this myelin sheath is formed by what? The Schwann cells in the peripheral nerve, oligodendrocytes in the central nervous system. The Schwann cells will lay down the myelin sheath. Myelin sheath is nothing but the cell membrane of the Schwann cell that is covering around the axons. So now in between the myelination, we call it as the node of Ranvier. So this is the node of Ranvier, and now here in this portion there is higher concentration of voltage gated sodium channels and potassium channels. Now let us explain how action potential, which is generated at this axon hillock or initial segment, action potential generated here, how it propagates now. So action potential generated with the initial segment, more and more positive ions are entering through voltage gated sodium ion channels, and these positive charges, they diffuse through the exoplasm. They diffuse through the exoplasm to the node of the Ranvier. And here in this portion, what is happening? Because of the entry of positive charge, the membrane potential from minus 70 millivolt resting potential is taken to firing level, that is minus 55 millivolt, and at this firing level large number of voltage gated sodium channels gets activated and action potential is generated in the node of Ranvier. That will result in more and more positivity inside the cell. From minus 55 it will go up to plus 30 millivolt, more and more positivity inside the cell. So the action potential here is jumping from one node of Ranvier to the next node of Ranvier. It is not electrotonic spread, but it is jumping action potential. Now once this area is excited, the positive ions, they diffuse to the next area. So here again, from the resting membrane potential, which was minus 70 millivolt, is taken to minus 55 millivolt because of the positive diffusion, positive charge diffusion. And at the minus 55 millivolt firing level, voltage gated sodium ion channels open up and action potential is generated. So you can understand by this diagram, this is a jumping nerve impulses from one node of Ranvier to other node of Ranvier. You call it as saltatory conduction. Saltatory conduction. And velocity of conduction here, when compared to that of the above diagram, what is the velocity of conduction here? Velocity of conduction will be more faster here in case of myelinated nerve fibers because of jumping action potentials, and action potentials are only generated at the level of node of Ranviers. So this is about propagation of action potentials from the site of generation of action potential till the nerve terminals. How the action potentials or the impulses spread from one region to the other region all along the surface of the cell membrane in case of non-myelinated or unmyelinated neurons, and in case of myelinated neurons. So the two types of propagation of action potential you understood: electrotonic conduction and saltatory conduction. So now we'll move to the last property of action potential, that is accommodation. Or adaptation. The fifth property, accommodation or adaptation. What is this? See, now for an action potential to be generated at a particular area, a threshold stimulus should be applied. So threshold stimulus means adequate in strength and adequate in duration, that has to be applied rapidly so that action potential is generated by influx of positive charges. So if at all you increase the strength of the stimulus slowly to firing level, if you increase the strength of the stimulus slowly to firing level, whether the action potential is generated, question mark. See, consider hypothetical values. A threshold stimulus that is of 3 millivolt applied for 3 seconds, action potential was generated. Now in this hypothetical, slowly if you increase the strength of the current, that means you applied 1 millivolt current for first second and you applied 2 millivolt current for the second and you applied 3 millivolt current for the third second, whether there is action potential generated. So for how long the current is applied here? The current is applied for, the stimulus is applied for 3 seconds. But the strength of the stimulus is slowly increasing. So does this generate action potential? Does this generate action potential? We'll explain now. So what happens when the current is applied slowly? So consider now from minus 70 millivolt. If you apply a 1 millivolt strength of current, only few sodium ions enters. It will not take the membrane potential to firing level. Only few sodium ions are entering. So there is slight depolarizing potential happening. And because the second 2 millivolt current is applied only after 1 second duration, there is a more duration time. In this duration, what is happening? The potassium efflux is also continued through the leaky channels. So because of the potassium efflux, the positivity within the cell that is going out, there is a decay of this. So this will result in adaptation or accommodation of the cell membrane, so that slowly if you increase the strength of the stimulus, there is no generation of action potential. Now if at all the second stimulus is applied here, it can take up the membrane potential from minus 70 only to a slightly higher levels, but not up to the threshold levels. Because again there is a time lag. In this time lag, what is happening? The potassium, even though sodium has entered and taken the membrane potential from minus 70 to certain levels, not up to the threshold level, there is continuous efflux of potassium through the potassium leaky channels. So there is a decay of this. So these are like graded potentials that are happening, but the membrane potential is not reaching the firing level. And action potential will not be generated if there is graded increase in the strength of the stimulus. This is like sawtooth current. When slowly increasing current is given, what is happening? When the slowly increasing current is given, the sodium entry is balanced by the leakage of potassium. So what happens to inside? It won't become firing minus 55. It will never become firing minus 55, and action potential will not be generated because of a balance between the entry of positive and exit of positive. So is that clear? Entry of positive sodium is balanced by the exit of positive potassium moving out. So that is why the membrane goes into a state of adaptation, and this is the phenomenon of accommodation. When slow rising current is applied, there is no generation of action potential. So this is one of the property of action potential. Thank you.